Okay, let's say we want to prove that the magnitude of the vector CV is C times the magnitude of the vector V. For this definition of magnitude, dot product. How are we going to prove that? And this could be in Rn. Well, we do that simply by replacing V with V1 through, in order n tuple V1 through Vn. So, on the left-hand side, we'll have the C times your vector V inside the magnitude signs, and then C times the vector V1, V2, dot, 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 Vn, magnitude signs. Got a little cramped there, but you understand what I've written, okay? Well, now we just write out what this means and what this means. Okay, well, the left-hand side, C times this vector is just CV1 dot 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 CVN. See, I'm already, and I have the arrows wrong. Okay? So we just multiply through by the C. Over here we have C times the magnitude of V1 up through Vn. And I haven't changed that yet. Okay, well now I'm not going to have room to write everything in one line, but we'll be able to do this. So what is this? This is just the square root of CV1, CV2, up through CVN, dot CV1, CV2, up through CVN. And that's equal to C times the square root of this, which is just V1, V2 through V sub n, dot V1, V2, dot V sub n. Well, dot products are easy to do, and I'm not going to write out the details of that. This dot product is what? It's the square root of, yeah, sorry, never mind, okay. Of CV1 times CV1 plus CV2 times CV2, all the way up to CVN times CVN. That's going to be C squared V1, and there are no vectors over the V1 through Vn. If I had vectors, arrows over these would represent column vectors, would represent matrices, and it wouldn't be right. And I did it over here too, so let's be just really careful about notation, okay? You do better than I do, okay? The arrow goes over the whole vector. Okay, well, when I do the dot product, then first component times first component, C1 squared, V1 squared, second component times second component, C squared, V2 squared. Well, that's just going to continue all the way up through C squared, V sub n squared. And that's going to be equal to what? C times this, which is V1 squared, V2 squared, etc. V1 squared plus V2 squared up through V sub n squared. Okay, now, is this equal to this? Well, yeah. We could get more detailed. The left-hand side, you have the square root of C squared times V1 squared plus up through V sub n squared equals C square root of V1 squared up through Vn squared. And then this will be the square root of C squared times the square root of V1 squared plus dot 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 plus Vn squared. And that's just C times this. So the two sides will be equal. So we've proven our result. Now, all we did was replace V with V1 through Vn, and then just did the arithmetic, the algebra. Okay, the only tricky algebraic point is factoring out the c squared. So we get a square root of c squared times the square root of v1 squared through vn squared, giving us this, from which we factor out the c squared, and the square root of c squared is c, etc. So it's just a matter of writing this down and then doing the algebra until we prove both sides equal. And that's really about all there is to most of these proofs. Some are more complicated, of course, than others.